Hello, in this video we'll talk about how delta G relates to the reaction quotient. We'll introduce a way to figure out the equilibrium constant from delta G naught, and then talk about how delta G and delta G naught relate to each other. Alright, so first up, here's something we talked about previously in the equilibrium chapter. So you can calculate a reaction quotient Q, and that is the same form as the equilibrium constant. It's just that instead of plugging equilibrium values of concentration in there, you plug non-equilibrium values, and then you can compare that to K to see which direction you're going to go. If Q is bigger than K, your reaction's going backwards. It's going from right to left. If Q is equal to K, you're at equilibrium. And if Q is less than K, then you're going to go normally from left to right. The same thing also works with Kp and Qp. I just wrote it with concentration. Now, delta G, which we talked about in the previous video, that also tells you about reaction spontaneity. So the ratio of Q over K and delta G need to be related. And they are, and I'll spare you the derivation. Here are the equations that do so. I do want to point out that there's no degree sign down here. And we'll talk about why that's important in a minute. And so again, you can do this for concentration, you can do it for pressure, either one's okay. And so delta G equals RT ln, this ratio of reaction quotient over equilibrium constant. And so what this tells you is, given some amount of reactants or products or what have you, which way is this reaction going to go when it proceeds towards equilibrium? Alright, so now the next step here is we want to figure out how to do this at standard states. And so remember, standard states are 1 molar and 1 bar. Do note that this does not specify a temperature. There's a reason why we wind up doing it at all at 25 Celsius, but this definition doesn't require that. Alright, we want to get to standard states because, first of all, the tabulated values for delta G are all at standard states, and secondly, it'll give us something useful with regards to K, and so we want to see what this does. So let's take a closer look at K here. All right, so here's our generalized reaction. Here's how the form of the equilibrium constant would look like. Now, if all concentrations are 1 molar for Kc, then you're plugging 1s into all of these, right? So that's what this looks like down here. And then since we plug a bunch of 1s in here, our reaction quotient is 1. When we're at standard states, the reaction quotient is 1. We gave it the degree sign now because we are at standard states, and that's what that little degree sign means. You could do this in terms of pressure just as well, no problem. So remember, because we're not at equilibrium, we're not calculating the equilibrium constant unless the equilibrium constant happens to be 1, which doesn't usually happen. So we're using Q here instead of K. Alright, so let's keep going with this. So let's take the equations that we had on the previous slide, and let's plug in this new thing. So say we're at standard states, so our reaction quotient is going to be equal to the standard state reaction quotient, which is equal to 1. And we can do this for both concentration on the left and pressure on the right. And so we get this. So we just plug this in, basically added a degree sign here, which puts us at standard states. The numerical value of this number here is equal to 1. And now delta G is now delta G naught. Because we're at standard states, this degree sign appears over here. So these two things are different. Alright, so now since Q is equal to 1, we can set it equal to 1. And then this also, in addition to doing the numerical thing, it also makes all the units go away, because usually equilibrium constants have units, although not always. And so you have the same units on the top and the bottom, and the units will cancel out. That's useful because we're sitting inside a logarithm, and you can't take a logarithm of things with units. So K here is now unitless, that's great. It has the same numerical value as we had before, that's Kc, and we represent it with just K. Now over here on the pressure side, well, we have the same thing. It was Kp, so now the same numerical value is equal to K, and then these two Ks are generally not the same, even though they're the same symbol. So that can lead us into problems, although this is kind of a nuance here. And so this same symbol K may equal two different numerical values, and so it's our job to keep them straight. And so, well, what we do is we say, if you're dissolved in water, then you use Kc. If you're a gas, then you use Kp, and there we go. So gone are the days of looking at gases in terms of concentrations. I mean, you can do that, it's just that your equilibrium constant won't equal delta G. So now we can simplify this. If you use a logarithm rule that tells you that if you invert something inside the logarithm, if you put a negative sign here, it's still equal to the same thing. And so we do that. We take 1 over k, which is just equal to k, and we put this negative sign here. And remember, since there's a degree sign here, this tells us this delta G is only valid at standard states. So this is why we wanted to get to standard states in the first place, because hey, it's equal to k. That's our equilibrium constant. That's a useful thing we want to know, right? So this equation relates delta G, the standard Gibbs free energy change, with the equilibrium constant. The fact that there's a degree sign here really matters. Before, when we were talking about delta H, the degree signs didn't really matter because effectively, well, you just use it and it worked out okay. And that's because the enthalpy value for your reaction doesn't really depend on the concentrations or the pressures, what have you. It just is for the reaction. So the degree sign there didn't really mean much. Now, since delta G versus delta G naught are very different, it does matter. So keep that in mind, right? We can use these previous equations, combine them together to get this lovely thing, which now gives us a relationship between delta G and delta G naught. And so the reason you would want to do this is because you can often look up or calculate delta G naught. And, well, but what if you're not at equilibrium or at standard states? What's delta G going to be? And so you can use this equation to find that out. And so let's talk about this a little more in depth, right? Is that delta G predicts spontaneity for wherever you are now in the reaction. Delta G naught is a constant for the reaction, and you calculate it from delta G of formation, which we'll get to in the next video. Don't forget to use the gas law constant in terms of energy. Q is our reaction quotient, okay. Delta G naught is fixed for a given reaction, because you have all the concentrations set or pressures set, and so one reaction, given standard states, has one delta G naught value. Whereas this other term is going to vary around as Q changes as your reaction proceeds until it's equal to K. All right, I'm going to just say this a lot of times and hopefully it sticks, right? This relationship between delta G and delta G naught. So the equations are at the top. Delta G, it tells you where the reaction is going to proceed forward or backwards, given your current conditions. So if you have 2 molars of this, 0.1 molar of that, some particular amounts or pressures of reactants and products, which way you're going to go. Delta G naught tells you if you have 1 molar of everything, which way are you going to go. And so they're very different. And so let's throw some numbers on this to help illustrate this difference. All right, so imagine you have some reaction that's happening under standard conditions. So if you put this equilibrium into an icebox, all the initial concentrations are 1 molar. So we want to know whether this reaction is going to go right or left or right, what have you. So we can get to this by looking at the form of the equilibrium constant, right? If K is bigger than 1, then if you start from everything equal to 1, you're going to make more products and less reactants. So it's going to proceed to the right and make more products. And so we call this reaction spontaneous under standard conditions. You start at 1 molar of everything. It's spontaneous if it goes to the right from there. And you'll have more products present at equilibrium than reactants. Your other option is your reaction is going to proceed left. If K is less than 1, it'll form more reactants than products. And so then we say that the reaction is not spontaneous under standard conditions because you put 1 molar of everything in there, it's going to the left. All right. Why are these two things useful, right? So delta G is useful for predicting spontaneity given your current conditions, whereas delta G naught helps you find the equilibrium constant, which often that's a really useful thing to be able to calculate equilibrium constants. And then if you happen to start at standard states, this will tell you which way you're going to go. Delta G and Q depend on concentration and will change as the reaction goes, whereas delta G naught and K are constant for a given reaction. And so you can convert between all of these. So I'll start in the top left. Your current state of your reaction, whatever concentrations or pressures you have, delta G. If it's negative from where you are, you're going to go to the right. You can convert this into Q, assuming you know what delta G is. So you convert it into Q, Well, if Q is less than K, you're going right. Q is bigger than K, you're going left from whatever your current position is Q. So the top two here are current, wherever you are at the moment. Now, if you want to go to equilibrium, well, at equilibrium, Q equals K. And so if K is bigger than 1, there's more products at equilibrium. If K is less than 1, there's less products and more reactants at equilibrium. And you can use this nice equation down here to convert yourself to delta G naught at the standard state, which tells us about the amount of products at equilibrium, right? So both of these can give us the same information of whether you have more products or more reactants at equilibrium. And then if you're at standard states, you can convert between these two. Okay, so a bunch of different equations going around here. So the more you practice this, the better off you're going to be. Let me just close with a couple quick examples of how to use this. And so say we're burning benzene and oxygen. It makes carbon dioxide and water. And you either looked up or calculated the delta G naught for this reaction. Again, we'll see this in the next video. You can use values in a table to calculate this number. Another reason why it's useful. So then here's the equation we're going to use. We'll plug our numbers into this equation. One big thing is you got to make the units match. Oftentimes delta G is in kilojoules per mole, in fact almost always. But the ideal gas law constant in terms of energy is just in joules. So whatever you got to do, make the units match here. And so we can do this and get some number that's equal to the natural log of K. Remember, if you want to undo the natural log of K, you just take e to both sides. So here's e to the natural log of K, which is just equal to K. And then the other side is e to the 2,584. And this number is so freaking big, it blows your calculator's mind. What does that mean? So that means that since K is so big, it means that effectively K is almost infinity, and you have all products and no reactants. Which, you know, makes sense because you're burning a flammable liquid, that reaction is going to go. And so when we first taught you reactions, most of the reactions were of this style, where it's a quantitative reaction as they all form products. And then now that we're moving farther along in chemistry, we realize that that's not always the case. Here, it is the case. You're going to make all products. Let's look at our last reaction here. So this is acetic acid. You put it in water, it makes H3O plus and acetate. And then we have the equilibrium constant for this in terms of concentration, which we call Ka. That sounds familiar, right? So let's see how this relates to the delta G naught. Here's the equation we're going to use. We basically just plug numbers into it. Okay. It'll give us out a number in joules per mole. And then we want to convert that to kilojoules per mole. It's a nice way to deal with the sig figs here. And so this is a positive delta G. So this reaction is not spontaneous under standard conditions. But you know that you're going to make some H3O plus because when you put acetic acid in water, it makes the thing acidic. So you are going to have some products around there, even though delta G naught is positive. And the reason here is because delta G naught refers to where the reaction is going to go if you put 1 molar acid, 1 molar base, 1 molar H3O in. So if you did all of that, yeah, this reaction is going to the left to form more weak acid. And so if you wanted to know how this reaction behaves in circumstances that we normally care about it, you'd use delta G. And then if you start with just the acid in a container, well, delta G, it turns out, is going to be very negative and very large, which means this reaction is going to proceed forward spontaneously until it reaches equilibrium where delta G is 0. Right? At equilibrium, delta G is 0. Delta G naught doesn't really relate to equilibrium positions of your present system. It tells you more what the equilibrium constant is for this reaction. Okay. So a bunch of ideas flying around here. Hopefully I was consistent in making the video and saying the word not where I meant to. However, if it said delta G naught on the slide and I said delta G, go with what the slide says. And that's all I have for now. Thanks for watching.